start with the first material of the day. But I need you to confirm if you guys are seeing what I'm projecting right now. Time series analysis part 2, the AR1 model. Can you guys see that now? What I'm
Yes.
okay. So thank you so much. Like I said, today is another important, topic to discuss about. Okay, and you know what? I could remember the other time I started we started a time series together. I actually introduced you to time series and some stuff, but today I'm actually gonna walk you through this outline. Number one, today I'm actually gonna give an example of time series data. Some of you have seen time series data, but maybe you don't really know whether it's time series or not. Okay, I'm gonna show you an example from medicine, economy, epidemiology, and so on like that. You're gonna see example on that today. Then I'm also going to walk you through what we call a time series graph. Time series graph is very, very essential. It's an essential tool in time series to be able to figure out some measures. Okay, some measures like whether we got a mean reversion or we got a time trend, the seasonality, and whether there's a structural breaks. Okay, so I'm actually going to show you how a time series graph can actually be used, you know, to investigate this. Then another thing I'm actually going to talk about today is the important concept in time series. I think I walked you through this the other time, but I'm still going to mention that in today's lecture, okay? Uh, and this important concept are the autocorrelation and the, stationarity, okay? But only that we're going to be talking about weak stationarity, okay? It's not going to be a straight one, okay? And I'm actually going to walk you through that today. And I'm also going to walk you through the simplest model in time series that we call the white noise model. So today, I introduced you to the white noise model the other time. I could remember in the last lecture, we actually simulated from a Gaussian process and we took some decision, okay? And you know what? Today, I'm actually going to tell you the significance of a white noise model in time series analysis, okay? I'm actually going to walk you through that today. And lastly, I'm going to I'm going to introduce you to what we call AR1. What is AR1? AR1 means autoregressive model of order 1, okay? I'm actually going to walk you through that as well today. So this is what I got for you today. All what I just need from you is just for you to be able to sit back and ask questions where you think that maybe you need some clarification. So I'm going to go into the example of time series data right now. And for those of you who really want to have access to the data, okay, you guys are in the middle of practical assignment where I ask you to choose the topic of yourself, and it has to come from where the area you are majoring. And you know what? Of course, um, or whether you want to choose from economics, you want to choose for social sciences, or epidemiology, medicine, or physical science. If what you are going to choose is a time series data, how does it look like? I'm actually going to, that's what I'm going to show you right now, okay? So under the economics, of course, the time series data that we have in economics, we could be talking about the gross domestic product that we call GDP, then the consumer price index, the S&P 500 index, and we could talk about, unemployment rates. All these are time series data. I could remember my bachelor project was actually on, I work on multivariate time series where I collected data set on gross domestic products, the consumer price index, the exchange rate, and the inflation rate. Okay, and I look at that. Though what I did was a causal relationship. I trying to study relationship. How the GDP of a country in Africa called Nigeria can actually be predicted from the knowledge of the exchange rate, the consumer price index, and the inflation rate. Okay, so if you want to have access to that, okay, the data that has to do with the GDP, the S&P, whatever, you can actually check US GDP from Federal Reserve economic data. Okay, you can actually check that. Okay, when you check this site, you're actually going to see some time series data. Okay, based on the GDP. Now, do you also know that the birth rate, when you're looking at the birth rate, the population data, the migration data, the political indicators, they are also example of a time series because these are data that are collected over time. Okay, these are data sets that are collected over time. If I take you back to the unemployment rate, in the month of May, United States of America added 250,000 jobs. Okay, sorry, 2.5 million jobs. I made a mistake. Added 2.5 million jobs in the month of May. If you look at the May report, okay, and which that was a surprise because in the middle of pandemic, you know, uh, that particular figure was not, uh, you know, was not near prediction. But I'm going to tell you as time goes on why we could have some surprises like that. Okay, and in the month of June, the economy recorded another 5 million jobs, and that actually twice the number of jobs, recorded in the month of May. Okay, so you know, looking at it, in a way that will affect the unemployment rate. In that situation, it means your unemployment, the unemployment rate was high during, at the beginning of the pandemic, because that was, part of the restriction imposed by the government is that, okay, uh, social distancing and a lockdown, okay? And you know what? Since then, the unemployment rate has been going very high, but you know, the recent news, okay, the May and the June news actually comes, uh, because of the addition of the new jobs, okay, in manifold, okay, that actually will have effect, will bring the unemployment rate down. And you know what? If you look at the birth rate, of course, over time, the birth rate of a particular country changes. And not only that, what about the population, okay, the migration, and some economic indicators, okay? If you really want to have data set on that, you can actually visit population without citizenship from, Eurostat, okay? You can visit either this or you visit Eurostat, okay? Then in epidemiology, you know, do you know that the disease rate, right now we're in the middle of pandemic, and you know what? Um, the we could find it this the rate of transmission of this disease, okay, from time to time, okay. So, and that is the reason why when you go to the worldometer, okay, or when you visit the website of the John Hopkins University, they monitor the incident rate, the number of cases of COVID-19 from, you know from day to day, from week to week, from month to month, from country to country, and from state to state, okay. So the mortality rate, the mosquito population, and so on like that, okay. So if you want to get a data set that has to do with this, you can go to US cancer incident rate, from the Center for Disease Control, okay. So when you take a look at that, it means we could get time series data in economics, in social science, in epidemiology, and in medicine. We could talk about tracking blood pressure, okay? You know, blood pressure is something that varies over time, okay? From time to time, like as you're looking at me right now, if I check my BP in the morning, okay? If I go back again to check on my BP, there's possibility that my blood pressure could have either gone down or even go up, okay? So depends on what I subject my body to or what I'm thinking about and stuff like that, okay? So the weight tracking, the cholesterol measurement, the heart rate monitoring, all these are example of time series data. And of course, if you open this side here, you're going to see some example of data set in that category, okay? Now, another thing that I actually want to talk about is the physical science, okay? The physical science, okay? You could look at global temperatures, okay? The monthly sunspot observation, the pollution levels. These are things that varies, okay, from time to time, okay? So I want to tell you that these are example of time series data, okay? If you really want to have access to a data set like that, I will advise that you visit the global air pollution from our world, okay, in data. So you're actually gonna get that. But let me tell you this: time series is one of the special concepts in statistical analysis because you know why? You know, because the statistical characteristics of time series, okay, often violate the assumption of conventional statistical method. I'm going to tell you that again, okay? So what I just said right now is that the statistical characteristics of time series often violate the conventional, okay, assumption of statistics. And the reason why there's that violation is because when you collect data set over time, okay, there's always going to be an assumption violation, okay, because we're actually going to have independence. We're going to have dependence. We're going to have a situation whereby what I record in one day may actually depend on the previous day. And that is the reason why that is actually going against, you know, the assumption, okay, of normal statistical, you know, the statistical model. And that is the reason why time series is a very special component in statistical analysis, because we know there's going to be an assumption violation of the conventional statistical means. And that is the reason why we actually need to have a careful investigation. We actually need to use a very special tool, okay, for us to be able to arrive at a very good result, okay? So, like I said, the statistical characteristics of time series data often violate, the assumptions of conventional statistical methods. Okay, so if that is the case, now that you guys understand, the example of time series now, the next thing I'm actually going to talk about is to move to what we call a time series graph. Okay, so what do we call a time series graph? I'm actually going to explain that to you right now. Okay, so let me tell you that it's a tool that we use, okay, in time series analysis to detect if data have these four. I'm going to say that again. We need in time series analysis, we actually need a graph called a time series, graph. And this time series graph will enable us to be able to investigate, to be able to detect, okay, whether there's a mean reverting or the series has an explosive behavior, okay. That's number one. I'm actually going to explain what we mean by mean reverting, okay? Then that can also be used to detect the incidence of a time trend, okay? Then we're also going to investigate for seasonality, okay? The time series graph can actually use to investigate that, okay? And we can also use that to investigate whether there's a, kind of a structural breaks in the process. I'm actually going to explain this one by one, okay? Now, because the knowledge of these four, okay, the knowledge of these four right now, can help, guide the testing, the diagnostics, and the estimation method, used during the time series modeling and analysis, okay? Because if we have the knowledge of these four, that will enable us to know the right model we are actually going to use. There's a lot of models in time series, okay, that we can actually use, but actually depends on whether we are able to investigate for the presence of all this. And not only that, the diagnostics, because when we have a time series model, and when we have any model at all, we actually need to subject that into diagnostic testing, okay, to be able to know whether a model is really doing a good job or not. Okay. And you know what, without investigating this for right here, it may be impossible to be able to do what I call model diagnostics. Not only model diagnostic, model testing, model estimation, and so on like that. And that is the reason why we actually want to do that. Okay. And you know what, I want to tell you right now uh, that you know the statistical characteristic, like I told you before, actually violates, okay, the conventional assumption in statistical model, okay. Therefore, we actually need, this particular tool that I call a time series graph, to investigate, okay. Now, like I said, I'm going to explain this one by one right now. I actually want to talk about what do we mean by mean reverting. I want to talk about what we mean by mean reverting. Let me tell you this. The price of a stock, the tendency of the price of a stock, to revert back, to change its direction, and come back to the average. Okay, that is what we call mean reverting. Okay, mean reverting is just that. Okay, you know what? Right now, when you talk about stock market, it's volatile. The price is volatile. Okay, there's a lot of volatility, okay, in the stock market because the price keep changing. Okay, it keep changing. I think you get it now. But what we're trying to say, on the long run, if the price actually converge to the mean price, okay, if it is actually converge to the mean price, then what we're actually going to say is that it is mean reverting, okay. And that is the reason why you know the specialists in the stock market, we actually normally console the investor that, you know what, you don't need to be panic right now. You can actually wait for the time, okay, that we're actually going to have a mean reverting, okay. And let me tell you something. What happened in the stock market is more or less like what happened when I have a coin. Take a look at a coin, okay? How many coins do we have in it? How many sides do we have in a coin? We got two coins. I mean, we got two sides, right? We got a head and we got a tail, okay? Now, when I flip it, of course, it's either I get a head or I get a tail, okay? Now, let me tell you this. There's what we call theoretical probability, and there's what we call experimental probability, okay? Now, when you look at the theoretical probability, Okay, the theoretical probability is that, okay, before I perform any research with a coin, I know the natural probability is half, is 1/2. The probability of any of the side showing up is 1/2. But you know what? If I go into experimental probability, when I take a coin and I flip it, there's possibility that in the first trial I may see a head. If I continue again, I may see a head. If I see number of head, if I toss it 10 times and the number of head, if the number of head that show up is 8, somebody is going to tell me that is 8/10. It means the probability of getting ahead is 8/10. And somebody is actually going to be telling me, is that not going against the theoretical probability that said that it should be 50/50? Okay, that should be 0.5. Let me tell you this. On the long run, when you continue to toad, when you continue to have a good number of trials, do you know that the experimental probability will converge to the theoretical probability? And that's exactly what is happening in the mean reverting, okay? Even if the price of the stock is volatile, if it keep on changing, okay, there's going to be a time that it's actually going to revert. Reverting is like it's changing direction, and it's actually going to converge to the mean price. And that is what we call mean reverting, okay? Now, when you take a look at what I have right here, now, if a model is mean reverting, if we use a time series graph and we get a mean reverting, then it's actually going to be telling us if I want to fit a time series model, it should be autoregressive model of order 2. Okay, now because it means in my model, when I have a reverting, okay, when I use a time series graph and I get a reverting, then what am I actually trying to say is that, the model, if you take a look at what I have right here, okay, this is a 0, right? Okay, you're going to see that most of what I have here is above 0. Okay, most of what we have here is actually above 0. If most of the point, if you take a look at that, is above 0, then it means in our model, we actually need to include non-zero mean. I'm going to say that again, because it is important to know whether a model should include a non-zero mean or not. And that is a prerequisite for determining appropriate testing and that I talk about the other time. So when I have a situation like this, where, most of the point right here, they are above 0. This is 0. This is a data set, that was plotted. This is like, the price, okay, the return of the price that was plotted against the number of years, okay? And you take a look at this, it means if I actually want to model this, I actually going to include non-zero mean in my model. Is there anyone who want to ask question now? So the mean reverting, if you take a look at what I have here now, we're actually going to see that most of that actually, they are above 0. Okay, and when they're above 0, then it means the time series model, in my time series model, I actually need to include a non-zero mean. Non-zero mean, okay? And that is what this is actually talking about, and that is what we mean by mean reverting, okay? And let me tell you this. In a situation, in a medical setting, okay, where a doctor is treating a particular patient, because the doctor at the end of the day, if they really want to know whether they have succeeded in treating the patient, they're going to have a measure, okay? And if they check there's something and there's something is, maybe it's BP, maybe it's something that is just going up, coming down, going up, coming down, it's just going in that way, okay? And the doctor is going to say, okay, he's going to wait for a time, this is actually going to converge to the, to the mean of a normal person, even if there's a volatility in the system right now. But one thing is to be able to tell what will be the number of time it's actually going to take for us to be able to have a mean reverting. And that is a major, that's another question in statistical analysis to be able to figure that out. Before the price we actually, get back, converges to the normal, to the average price. Before, what it takes for the variable of my patient, what the patient that I'm treating right now, to be able to converge to the normal, to the variable of a normal person in terms of the average, because there's going to be a threshold, okay, before a particular doctor will claim that he has succeeded in treating a patient. He has to compare, the variable, the average, of the variable of that person with a threshold. When I say threshold, there's going to be a value for a normal person, okay, before he can actually boast, okay, you know what, I've succeeded in treating this patient. Okay, so the next thing I'm actually going to talk about is time trading data, okay. I told you something the other time, that one of the questions the time series graph want to answer is whether there's there's a presence of the trend in the data, okay. When you take a look at this one now, I actually plotted the price, against the number of years from 1960 to 2000, okay. I think you can see that right now, okay. Now, if you take a look at what I have right here, you're actually going to see that this is more or less having a trend, because you can see the way it's like having a positive trend, because it'll keep going up, okay. Now, in addition, the other time in the mean reverting, I said, okay, uh, we see situation whereby we said, okay, if that really happened, we actually going to, consider what I call not zero mean in the model, okay? But in the case of the trend, in addition to having a not zero mean in the model, okay, we actually want to be able to investigate the trend. When I say trend, I mean the directional movements over time, the directional movement of the variable over time. Is it going to be increasing, or is going to be decreasing, or is going to be, it's going to remain stagnant, okay? So that's exactly what I'm trying to talk about, because the time trend in time series data, okay, also have implication, okay? It has implication for testing and modeling. And that is the reason why we actually need to investigate, okay? So now you can see what actually happened here. You're talking about this actually have a trend. Now, the next thing that we want to talk about right now is what we call seasonality, okay? And what do we mean by seasonality? Okay, we need to investigate. The time series graph can actually be used to investigate whether there's a seasonality, in the data, okay? Now, and what do I mean by seasonality? Okay, the seasonality occur when the time series data exhibit regular and predictable patterns, okay, at time interval that are smaller than a year. That are smaller than a year. Maybe something just maybe there is something that happened, in the corresponding months of the years under investigation. Particularly, if we want to talk about visitors to the other time, I show you visitors, the number of visitors in some selected years to the Mississippi River. Okay, now if we have uh, if we have a monthly uh, aspect of that data, okay, maybe in the month of November, maybe what happened in the month of November, it may be the same thing, similar thing happened in the month of November. And you know what? November in the United States actually fall in the month of Thanksgiving, where a lot of people will like to go out, okay? And you know what? Maybe I look at a particular store, like a Target or, Target, Walmart, and so on like that. And maybe in a particular month of the year, you know, they used to have a lot of customers. And that month could be the month of November because that's a month of Thanksgiving. It's a month of Black Friday. Okay. So when you're talking about seasonality, okay, your time series data set may exhibit what I call regular and predictable pattern at time interval, okay? And you know what? This time interval is usually smaller than a year, okay? And you know, and let me tell you this, an example of a time series with seasonality is retail sales. Retail sales often, they used to be increased between September to December, and this will decrease between January to February. When you're talking about retail sale, I'm going to say that again. Between September and December, there's going to be an increase. But you know what? From January, between January and February, there's going to be a decrease in the retail sales. Okay? So these are attributed to seasonality. Okay? Because what happened there is even less than 1 year. Okay? And that was why I said seasonality occur when time series data exhibit regular predictable pattern, okay, at interval that are less than a year. Okay, so that is seasonality. Okay, if you take a look at what I have right here, this is an example of seasonality. Okay, it's an example of that. Now, another thing that I want to show you right now is what we call structural breaks. Now, let me tell you something. Something that is actually, maintaining kind of pattern can, won't suddenly jump up, or it could be something, it could be sudden, it could suddenly jump down. If you take a look at what I'm trying to show you right now, this is an example of a of a structural break. Take a look at the pattern right here and look at what happened, at the beginning of 1980. Can you see what happened? And it's just jump up, okay? And when it's jump up and it stay for a very long time in that level, can you see that? This is an example of a structural breaks. Okay, I want to tell you that in structural breaks, I want to tell you that the global warming. Okay, one of the evidence that there's been a structural break. If you look at the climate experts are really claiming, they're advocating, the people that I call the climate advocate, they are trying to say it's like things have drastically changed in terms of climate. Okay, so that is one of the evidence of that. But another evidence that I also want to talk about is when there's a sudden change in behavior. This is like what happened right here. It's like a sudden change in behavior. Look at the behavior before. Look at what has happened now. Okay, a sudden change in behavior. Okay, at a certain point in time. Okay, and for example, we actually see so many macroeconomic indicators that changed sharply in 2008. After the start of a global crisis, there was a global economic meltdown in 2008, and this actually caused a structural break. I think you understand that right now. And you know what? The structural break can create instability in the parameters of a model. The parameters are no longer going to be stable, okay? Because the parameters right here is actually going to be different from the parameters right here. If you take a look at what I'm trying to talk about right now, and you know what, I'm actually going to give you the example of what I talk about. I've mentioned the climate change, and I've already told you identifying structural break in global temperature, has provided support to proponents of a global climate change. And not only that, the global financial crisis of 2008 is another evidence of a structural break. Okay, and let me tell you this. I want to give you another example right now from politics. Is there any one of you who is not familiar with the politics in the United States of America? Is there any one of you, can somebody confirm to me right now, because I want to talk about the former President Bill Clinton and the former President W.H.E. Bush. Has any one of you heard about the two names that I mentioned right now? Has anybody, okay, let me read my charts. Okay, somebody say yes, yes, yes. Oh, good job. So which means some of you have heard about the former President Bill Clinton was a Democrat, is a Democrat, and the W.H.E. Bush, okay? Now, let me tell you this. In 1991, the W.H.E. Bush was the president of the United States of America, and he is a Republican. Now, there was a war in 1991 in Kuwait, and America recorded success in that war, and the majority of the citizens, of American citizens, approve the job, the job performance of President Bush. In fact, 90% of the potential voters actually claim they're going to vote for, for President Bush again. That was following the war, the incidents of war in Kuwait in 1991, the success recorded. But you know what? Some more to the election in 1992, the economy of the United States got into recession. Suddenly, the economy that was performing suddenly got into recession. There was a structural break. Okay, and Clinton then was a candidate of a Democratic Party, and he took the advantage of the situation to unseat the incumbent. And I could remember the slogan used by the campaign director of Bill Clinton then. He called that economic stupidity. Has anybody heard about economic stupidity? Have any one of you heard about that? Can somebody in economics among you confirm if you have heard about economic stupidity before? Economic stupidity. That was the word used by the campaign, that this economic was stupid, that we actually need to do, you actually need somebody that will, that will make the economy to bounce back. Okay, then I want to put it to you, and he successfully used that to unseat the then president, the incumbent president, and the Bill Clinton was elected American president because of the fact that there was a structural break, okay, in the economy as at that time. Okay, suddenly, things went disarray. So having a sudden, and it's maintained, and when it happened, it maintained that position for some time. So just to be able to tell you another example of a structural break. Now, is there anyone among you today uh, who doesn't understand the meaning of structural break, or the meaning of seasonality, or the meaning of mean reverting data, or you need a more interpretation or more clarification on the time trading data? Is there anyone who, because I'm done with this first material, I want to go into another material right now, and that is, excuse me, and that is the reason why I'm trying to ask whether you understand what we mean by structural break, whether we understand what we mean by seasonality, whether you understand what we mean by time trading data, or whether we understand what we mean by mean reverting data. Is there anyone? I need more clarification. Okay. Silence implies that you guys are good. Okay. And I'm going to stop my share right now. And I'm actually going to go into a new share. Okay. And that is going to be the second material for the day. Okay. So I'm going to share that with you right now. So the second material for the day. Now, I need you guys to confirm this material right now. Time series analysis part 2 AR1 model. Can you guys see that now?
Yes.
Yes.
Okay, thanks for confirming that. Okay, this is going to be a second material for today. Like I said, these two materials have already been attached. Okay, you can check the model. Okay, so in this second material, I quickly want to remind you of what we did last time. The last time we did the two concepts in time series analysis, which I'm still going to talk about today. Okay, it's part of the outline for today. And the two concepts in time series analysis is autocorrelation and stationarity. Okay, I'm actually going to walk you through this today. Okay, we talked about this last time, but today I'm actually going to relate this to real life. I don't want it to be abstract. I want you to be seeing what you are learning, okay? Because when you are seeing what you are learning, you're actually going to understand very well. Then I'm also going to walk you through the simplest time series model that we call the white noise model. And I'm also going to tell you the implication of the white noise model in time series analysis, okay? I'm going to walk you through that as well. But you know what? I want to start with a white noise. I want to start with a white noise, okay? And I told you before what we mean by a white noise. Now let me tell you this. What do we mean by white noise? If a model is a white noise, I'm going to say that again. It's a model. It's if what I'm generating, maybe I'm generating revenue, or I'm considering the number of customers that visit my grocery store, maybe daily, weekly, or stuff like that. If I'm considering a tiny time series data, okay, and if my conclusion is that it's a white noise, then the white noise means there is no connection between two time series data at two different periods. And what do I mean by that? I'm actually going to tell you right now. It means if I haven't have the knowledge of what happened on Monday, I cannot tell. I cannot tell what is going to happen on Tuesday. That is if I'm working on daily, okay? If I'm working on monthly, if I have the knowledge of what happened in January, I cannot say about what is going to happen in February, okay? So which means I cannot say whether what is going to happen next is going to be negative, or is going to be positive, or is going to be low, or is going to be high. That is what we mean by white noise. Okay, that's exactly what we mean by white noise. And that is the reason why we said, you know what? The mean of a white noise should be 0. And this is the variance of a white noise. So white noise is more or less like a shock. It's more or less like a surprise. It means what happened next is entirely, it's a surprise because we cannot predict that. It's unpredictable. And we don't want a situation like that. We don't want a situation whereby our model is actually going to be a white noise. We don't want that. We don't want a situation whereby our model would be entirely be a white noise. But you know what? White noise should be part of our model, but it shouldn't be entirely the model. I'm going to say that again, because we know that in any statistical model, there must always be an unexplained variation. We know that, okay? But in a situation where the series, okay, in a situation where the series is the same thing as white noise, then it means that you have a model where that model cannot explain anything. It means, you cannot explain what is going to happen next. You cannot use that model for prediction. And that is a situation where the model is entirely a white noise. But we want a combination of a signal and a white noise in a model. That's exactly what we want. We don't want a white noise alone. Okay? And if you take a look at what I have right here, you're actually going to see that this is a combination of a signal and a noise. Okay? Because in a situation where this guy is a zero, of course, my model will be entirely be a white noise. It's going to be a noise, and you can never use a noise to predict. But we want to appreciate the fact that a white noise must be part of the model. Now, I want to tell you the reason. Why is it that the white noise must be part of the model? I'm going to tell you number one, I'm going to tell you the general reason. Number two, I'm going to tell you statistical reason. Now let me start with number one. We are in a world where we actually want to understand situation around us. Not only that, we are curious because of the variation in the world. Okay, because of the variation in the world, we are curious about what is going to happen next. We are so anxious. We want to know before we get, before the future. Can we have a way to predict the future? Can we have a way to do that? And you know what? If we really want to do that, we actually need to make use of a model. We need to model reality. Okay, and you know what? When we model reality, our model cannot give the exact picture of reality. I'm going to say that again. Our model cannot give exact picture of reality. There's always going to be unexplained variation that we call noise. There's always going to be a noise in any model. And that is having a noise in a model. Now, another reason that I want to talk about, having a noise in a model will enable us to be able to investigate the performance of that model. You remember what we did before, that in regression modeling, what we call residual analysis. Okay, we do the residual analysis when we are trying to investigate the adequacy of the model, and that is the reason why in any statistical model there must be a noise. If there is no noise, then we cannot do residual analysis. Then we cannot tell how significant, how adequate, how appropriate is a model. So I'm going to call that. I'm going to have a new share with you right now. I'm going to have a new share because I need to, to be able to tell you Can you guys see my whiteboard now? Can you see my whiteboard?
Yes.
Okay, now I'm actually going to call that for having reason for having noise in time series model. So why do we need to have a noise? Like I said, the model shouldn't be entirely noise, okay? But I'm going to tell you the number one is predictability, okay? Predictability, okay? Can you see that now? Predictability, I'm going to explain that. The number two is diagnostics. Diagnostics. And I'm going to explain that one by one. I'm going to start with the predictability. Now, let me tell you this. If your model is white noise, if your model is entirely white noise, then it means you cannot use that model to predict the future. I'm going to say that again. If your model is a white noise, okay, because the white noise is actually suggesting that there is no connection. It means what happened is purely random. The occurrence of any event is purely random. Anything can happen. Anything at all can happen. It could, it's actually going to be a surprise. You cannot tell about the future, okay? You can never tell. For instance, if I happen to be a manager in a grocery store, okay, if I make $10,000 today, I cannot tell about what I'm going to make tomorrow. So what I'm going to make tomorrow will be it's going to be a surprise because there's no connection with what I'm making at what I'm making at today at different period. Okay, and that is a situation where it's an entirely white noise. We don't want that. Okay, you cannot predict. It will lead, you are not going to be able to predict what is the essence of having a time series model. Of course, the essence of building a time series model is to be able to use the variation in the past, okay, to explain the variation in the future. I told you something the other time. One former American president, JF Kennedy, said, and I quote, "We cannot correct the past, but we can run perfectly the future through the mistake of today." That's exactly what we do. And that is the essence of having a model. Can we have a way to predict the future based on what has been happening? We can only predict the future based on what has been happening if there's a connection between what has happened before and what is going to happen next. Then another thing, another significant, another importance of a white noise in the model is diagnostics. Let me tell you this. When we want to evaluate any time series model, we do what we call diagnostics. And just like it is similar to what we did in regression analysis, we are in an attempt to investigate the adequacy of a linear regression model. We try to conduct what we call residual analysis, okay? And you know what? We do the same thing in time series model. And you know what we investigate? What we're going to investigate is a white noise. If the white noise, okay, I'm going to say that again. If the white noise of the model that we are using, if the random component, okay, is a white noise, okay, if the white noise behave normal way, and what is the behavior that I want the white noise to be? I want the white noise to be purely random. You remember in residual analysis, okay, there's a particular plot. If that plot is random, that suggests linearity, okay? And you can also use that plot to be able to figure out whether there's a constant variance. We also have it in time series analysis, okay? So we expect the white noise to be purely random. If the white noise is purely random, then it means whatever we want to predict with the model is actually going to be valid. Okay? And that's exactly what we're trying to talk about. Now, I've given you two reasons why the noise, white noise, have to be in a time series model: predictability and diagnostics. Now, I'm actually going to stop my share right now. Somebody said, is the variation due to the random error or hidden or no? I don't get what you mean clearly. But if what you're trying to say is, when we say random error means white noise, that's exactly what I'm trying to say. The errors have to be random, has to be purely random before we can call that a white noise. Otherwise, if a white noise is not purely random, and there's a way to tell using a graph, if it is not purely random, then we are going to say, you know what, this model is not adequate because we expect the white noise to be purely random. I don't know if I've answered your question now. Somebody who said, is a variation due to random error or something like that, okay? Now, I'm going to go back to my material right now. I was talking about a time series model that can be decomposed, okay, where the response in a time series model can be decomposed into signal and noise. You remember what we did in linear regression, where we decompose the response into explained variation, into unexplained variation. You remember that? We also have the same thing in time series analysis, okay? Now, if you take a look at what I have right here, what I have here is what we call autoregressive model of order 1, because I'm actually looking at the connection between the current and the immediate past. And that is symbolically, that's exactly what we talk about AR1, autoregressive of order 1. When we're trying to study relationship between the past and the immediate past. Okay, and that's exactly what we're trying to do right here. Take a look at that, and you know what, this part is the signal part, okay, and this part is a white noise, okay, and the white noise is assumed to be normally and identically distributed with a mean zero and sigma squared, okay. And I'm trying to tell you it's similar to what we did in simple linear regression model, okay. So take a look at that. This is a systematic part of a simple linear regression model, and this is a random part. Okay, so going by the data set that I used the other time, suppose the YT equal to this, okay, we got the model of order 1. Okay, this is the model for the daily revenue from an ice cream store. Daily revenue from an ice cream store. Every day, they got a record of the revenue from the sale of ice cream. Okay, so what I'm trying to talk about now is that the daily revenue, YT, is the daily revenue of the, from the sale of ice cream, is a combination of a signal and a noise. So both the signal and the noise are the one explaining that. That's exactly what we're trying to say. And that was why I said if the signal part is 100, the noise, and the noise is 2, then automatically what I'm going to realize is actually going to be 100 plus 2. And that is why I got 102. But you know what? What explains much out of the signal and the noise is the signal. This is 100 and this is 2. And if you take a look at that, and that's exactly what we have from time to time. So what I'm trying to show you in this table is just to tell you that, you know what, a particular response that is a time series variable has 2 components. Okay, you got a signal component and you got a component, I got a noise component. That's exactly what I'm trying to say right here. Okay. Um, I want to revisit what I talked about the other time to be the white noise. If I now want to basically talk about white noise model, where the YT can only be explained by white noise, there is no signal. There is no signal in this model. No signal means there is no connection between any two time series at two different periods. Okay, there is no connection. And if there is no connection, then it means I cannot use this model to predict what is actually going to happen next. And that is not good at all. And take a look at this. I showed you something the other time that has to do with my sleeping hours. I call that, daily sleeping hours for Kazim. Can you see that now? And my daily sleeping hours equal to YT plus WT plus 8. Okay. And you know what? This is a white noise. Okay. It's a white noise because you know what? If I sleep for a certain number of hours today, it means I cannot predict the number of hours that I'm actually going to sleep in the next day because I got a white noise model. Okay, and this is an example of the white noise that I talk about. If you look at the green line, the green line is actually going to be the average of the model. If I want to find the average of the model, what is the expected value of YT? Okay, the expected value of the YT is going to be expected value of WT plus expected value of 8. And expected value of a constant is a constant, and the expected value of WT is a mean, and which is actually 0 right here. It means on average that will be 8 hours. So this is an example of a white noise model. And you know what? I showed you the other time, if you really want to generate some set of data set, okay, that will look like a white noise, then you can actually generate that from a standardized normal distribution, okay? You can actually do that. Okay. Now, I'm just trying to show you right here, for instance, when I have in the model, okay, I got a YT equal to W2 plus 8, okay? And I actually want to figure out the mean. What does it mean? What is the expected, value of the YT, okay? And I'm actually going to do expected value of YT equal to expected value of the whole of that, because the YT equal to WT plus 8, okay? And you know what? When I do that, of course, the expected value of WT plus 8, the expected value of WT is 0. I told you right here. Expected value of WT is the same thing as the mean of WT, okay? And the mean of WT is actually going to be equal to 0. And at the end of the day, 0 plus 8 is actually going to be 8. And you know what? If I want to figure out the variance, okay? But you know what? Before figuring out the variance, I already know for a white noise process, the variance is supposed to be 1. Because we are actually going to be, the white noise process follow a normal distribution, okay? And a standardized normal distribution for that matter is going to have a mean 0 and variance 1, okay? But you know what? The mean of 0 that we have is for the white noise. The mean of the white noise and the mean of a model with a white noise, they are not going to be the same, but they're going to have the same variance. I'm going to say that again. When I have a white noise, which is the WT, and you know that the time series variable Y here equal to WT plus constant, okay? They're going to have the same mean. They're going to have different mean. The mean of the white noise is going to be 0, but the mean of the YT is going to be 8. That's exactly what I show right here. Look at that. The mean of the YT is going to be 8. But the mean of WT, which is a white noise, is going to be 0. It means the YT and the WT, they're going to have a different mean. But you know what? Statistically speaking, it is statistically proved and mathematically observed that, you know what? The variance, they're going to have the same variance. The variance of WT, which is a variance of the white noise, is going to be equal to 1, and the variance of a time series variable is also going to be equal to 1. And that's exactly what we show right here. the variance of WT plus 8. The variance of WT is going to be 1 because the variance of a constant, is 0. A constant doesn't change. And you know what? If I expand what I have here, if I want to use statistical theory, I'm actually going to have the variance of WT plus the variance of 8 plus 2 covariance. I'm going to have 2 covariance, WT and about, you know what? The two of them, we have said there is no connection, and that covariance will be equal to 0. And I show you the other time, I show you in the last lecture, when you're trying to find the autocorrelation at lag 1 or at lag 2 or at whatever lag, it's actually going to be equal to 0 because we are talking about situation where the time series variable are strictly independent. They don't have connection. Therefore, the correlation at lag 1, the correlation at lag 2, the correlation at whatever lag is actually going to be equal to 0. I demonstrated this to you in the part 1 of our lecture. Okay, like I said, we're going to be focusing, we are actually focusing on the autoregressive model of order 1. Like I said, the AR is autoregressive. What do we mean by regressive in English? I'm going backward because I'm trying to look at the connection between the past and the present. That's what we're trying to do. We're going, retrogressive, okay? And believing that the combination of these can actually be used to predict the future. And that was why I said, the one that you have here means that, only the most recent past observation, which is the YT minus 1, is used to predict the YT. The YT here is actually going to be the current value. Okay, I'm trying to link the immediate past of that particular value with the current one, okay? That's exactly what we're trying to do. Okay, so we're going to have a model for AR1 right now. And I'm actually going to walk you through the condition under which the AR1 is estimable, okay? I'm actually going to give you the condition under which the AR1 is estimable, okay? So what I want to walk you through right now, I need you to be able to apply your knowledge of algebra, okay? Because we're going to do some derivation right now, okay? And part of this will be tested in exam. So I actually want you to, to go with me in the way I'm actually going to be explaining that right now, because we're actually going to make use of, so not the knowledge of algebra, okay? Particularly algebra 1, algebra 2. Okay, but you know what? You don't need to panic. I'm actually going to walk you through that. Now, if you take a look at what I have here, this is an autoregressive model of order 1. Okay, the autoregressive model of order 1 will actually include a white noise. I told you before, all time series model must include a white noise because for us to be able to do for predictability and for diagnostics. Okay, and you know what? The white noise must be normally and independently distributed with a mean 0 and and the variance. Okay, now let us have an example right now where the C0 and the C1 are the parameters. In the linear regression model, you got parameters, right? We got the beta null, we got the beta 1, and so on like that. We also have parameters in an autoregressive model of order 1. And you know what? These parameters, the C0 and the C1, need to be estimated. I'm actually going to walk you through how we can actually estimate the parameters, okay, in autoregressive model of order 1. But here I'm just assuming that, okay, the parameters has already been estimated, the C naught equal to 0.8 and the C1 equal to 0.9. But you know what? In the autoregressive model of order 1, the C1 must lie between 0 and 1. Okay? It should be greater than 0 and less than 1. Okay? So I'm actually going to tell, and at times it could be negative. Okay? It could be negative. Okay, now alternatively, what I have right here, I can also write it in this form. Okay, there's another way to write that. Okay, there's another way you can write that. Okay, now going by the one we're working on now, take a look at this. If I give you something like this in the exam and I say, okay, obtain the mean and variance. If I give you something like this in the exam, okay, this is an autoregressive model of order 1. And maybe in my question, I say, okay, obtain the expected value of yt, which is the mean of yt. And I can also ask you to, you know, to obtain the variance of yt. Okay, I'm going to walk you through that because you know why? Getting the mean and getting the variance, we actually go a long way in answering a question, okay, that has to do with the stationarity. Okay, and you know the other time I introduced you to what I call stationarity. Okay, stationarity means there is no systematic change in mean and variance of the time series over time. Okay, of the series over time, there is no systematic change in the mean and variance. I showed you last week, you know, the mean have to be the same across board, the variance have to be the same across board. But let me tell you this, the estimability of parameters in the autoregressive model of order 1 actually rely on the assumption of weak stationarity. Because for us to be able to estimate parameters in the autoregressive model, you know, I'm talking about, you know, getting these values and this value, because here I'm just assuming the values have been obtained. But what I'm trying to tell you right now, for you to be able to obtain the values right here, there is a condition that is imposed on the model. There's an assumption that is imposed on the model, and that very assumption is an assumption of stationarity. We got a way to investigate that. But right now, there is something that is linked with that assumption, and what is linked with that assumption is, you know, getting the mean and getting the variance. And I'm actually going to walk you through the algebraic way, you know, how to find the mean of the process. Okay, now if you take a look at what I have here right now, this is an autoregressive model of order 1, and the question is like obtain the mean and the variance. Now I want to start with the mean. Mean is the same thing as expectation. Okay, now I need to take, if I want to find the expected value of yt, I need to find the expected value of everything right here. Now take a look at that. I'm taking the expectation of both sides. And don't forget, when I take the expectation of both sides, of course, I'm actually going to apply what you did in high school, particularly in Algebra 1. Okay, when you were in ninth grade, you did something that we call, you know, when you try to multiply. Okay, when you use, you know, you get a number in the parentheses and you get a particular number outside the parentheses, then you're actually going to use that to multiply everything. So right now I get the expectation outside the parentheses, and that will multiply each of that, and that is how I got this. Expectation of a constant is a constant. And that is why I don't need to write the expected value of 0.8 right here, okay? Because the expected value of a constant is actually going to be a constant, okay? Expectation will attract, you know, a variable. I'm going to say that again. Expectation attracts a variable, okay? The expected value of a constant is actually going to be a constant. And take a look at that. You can see expectation attracts a variable. Can you see that now? And you know what? Under the assumption, expected value of WT is 0. So it means if I plug in a 0 here, what I'm going to have now is just going to be this guy. Take a look at that now. Oh, that is what we have. Now, to be able to move forward, it means what I have right now, I got the expected value of YT equal to 0.8 plus 0.9, expected value of YT minus 1. The YT minus 1 is the information available in the previous past. The average, this is the average of the information available in the previous past. And this is the average of the information that is available right now. Okay, and under the assumption of stationarity, because we need to assume stationarity. Under the assumption of stationarity, you know, the on average, you know, the value of the time series right now must be equal to the of the previous values of that. So here, where I get the expected value of YT minus 1, I'm actually going to substitute expected value of YT. And that is the reason why I'm going to have expected value of YT equal to 0.8 plus 0.9. Then this guy is now going to become expected value of YT. Can you see that now? Is there anyone who doesn't understand how I go from here to here using stationarity assumption? Is there anyone who doesn't understand? Are you guys hearing me?
Yes.
Thank you so much. Thank you for confirming that. Okay, so I think the silence implies that you guys are good. Now, what I just need to do right here, I just need to solve linear equation. What am I solving for? I'm solving for the expected value of YT. And at the end of the day, look at what I got. My result is actually going to be 8. And you know what? We got here to be the mean of this process. Okay. Now, there is a pattern here that I'm actually going to show, that I'm going to tell you about in the future. There's a pattern here. I'm going to tell you about, there's a pattern here, and this particular pattern here, you know, actually give us the picture of something, and I'm still going to tell you that. But before I talk about that, you know, let me talk about the variance. Okay, if I want to get the variance right now, it's actually going to be the variance of that, okay? And you know what? This is a constant. The variance of a constant is 0 because a constant doesn't change, okay? And that is the reason why this is the same thing as this guy here, okay? Because 0.8 is a constant, it's independent of its variable, okay? And therefore, this guy equal to this guy, okay? Now, if you take a look at what I have here, the variance of an entity plus an entity should be equal to the variance of that entity, you know, and we need to consider the variance covariance, but we have an assumption. The covariance will be equal to 0 because the YT minus 1, you know, the YT minus 1 that we have and WT are assumed to be independent. So if they are independent, we're only going to have the variance of the can be splitted into this. Look at that. I'm only going to have that, okay? And you know what? If I have this one right now, if a constant want to come outside the variance, if I want the constant is 0.9, it's a constant here. If this guy want to come out, it's going to be squared. According to the statistical rule, I'm going to have a square of that. So that when this guy leaves right now, I'm only going to have the variance of YT minus 1. Now take a look at what I have, right? And you know what? What is the variance of WT? That has been specified. I'm going to, you know, what is the variance of WT? Look at that. It's 0.19. And we have already, so, you know, immediately you are given this. We have, you know, specified that WT equal to this. Okay, this is the variance of WT, okay? So I'm actually going to plug that into that. Instead of variance of WT, I'm actually going to put it 0.19. Okay, when I have is, so this is what I have right now. And you know what? We're going to make an assumption again. What is the assumption? The assumption is stationarity assumption that, okay, I'm talking about variance right now. The variance at two different time period have to be the same. So therefore, in order to move forward, I'm actually going to, say, since yt is stationary, okay, the variance of, the variance of the current value has to be equal to the variance of the past value. In that situation, where I have the variance of yt minus 1, it's actually going to become the variance of yt. Okay, so if I want to rewrite my equation right now, I'm going to write the variance of yt equal 0.9 squared. Instead of writing the variance of yt minus 1, I'm actually going to write the variance of yt plus that. Oh, look at what I have right now. I can now solve for the variance of yt. So the only thing for me to do is to solve the equation. And that is the reason why you need, what you are doing, what you did in the high school is not a waste. What you did in the middle school is not a waste. What you did in the elementary school is not a waste, because in a college, in the university, you are still going to apply, the knowledge of the high school, the knowledge of the middle school. And so look at where we find ourselves right here. We actually need to solve equation. What you were doing in the high school then may not actually make sense to you. I could remember when I was teaching in a high school, because I taught in a high school before in 1997, 98. When I taught in the high school, when I taught in mathematics in the high school, some of my students used to ask me questions. What are we doing here? It doesn't make sense to us. Why are we solving this equation? But right now, it's making sense, because we're actually applying that. And that is the reason why I said, knowledge at any level is very, very crucial, okay? And that is the reason why you pass through that experience. Okay, now we derive our variance of yt, okay, to be equal to 1. So, but you know what? There is something that I want you to see, and I want to generalize. And you know what? I'm actually, we've gotten the, the mean of the, of the ARO of autoregressive model of the one, based on what we are given right here, we got the mean to be equal to 8, and we got the variance to be equal to 1. Okay, but you know what, there is one pattern. Okay, there is one pattern I wanted to see right here, and that I want you to see right here. Okay, in a root to the value for the mean, I want you to look at this pattern very well. I'm actually going to be using that, and I also wanted to look at the pattern very well. I want it to be, I'm going to talk about that. Okay, I'm going to talk about that. Now, before I come talk about that, let me tell you this. Let me just talk about it right now. What do you have here? Is 0.8. Is 0.8 is representing what? That should be C naught. Look at that. This is C naught, right? Do you remember the general model? I'm going to show you the general model. Is that not the C naught? Okay, that's going to be the C naught, right? And this guy is the C1, right? Okay, there's something I want you to see. It means what I have right here is a combination of a C naught and a C1. If I want to write a general formula on this, I'm actually going to say C naught equal 1 minus C1. It means the moment you are giving the model right here, instead of going through all this process, I can actually say, okay, if I want to get the mean, I just need a combination of a C naught and a C1. Okay, the C naught is going to be the numerator, it's going to be at the top, and the 1 minus C1, okay, that's exactly what we have. Look at that. Instead of you to go through this rigorous process, okay, that is a power that I actually wanted to see. And when you look at the variance, you're going to see that the variance right here It's just, what do you see here? What is the 0.19? That is the variance of the white noise. Look at that. I'm going to show you. Look at that. The variance of the white noise, okay, divided by the variance of the white noise, the variance of the white noise, give me 1 second. The variance of the white noise divided by 1 minus C1 squared. Can you see that now? The variance of the white noise. If you want to skip, if you really want to check, though I need you to show your work, okay? But if you really want to if you really want to check whether your answer is right, do you know that the formula is basically, so let me tell you, based on this, and on this, I'm going to show you this as a pattern. I'm going to show you something now. Give me 1 second. I'm going to show you. Oh, look at that. Can you confirm if you are seeing this right now?
Yes.
Okay, it means if I want to figure out the mean of autoregressive model of order 1, this is the formula. C dot divided by 1 minus C1. And the variance of that is actually going to be the sigma squared, which is the variance of the white noise, divided by 1 minus C1 squared. And you know what? There is something that I want you to see here. It means for you to be able to estimate the mean and variance, then the value of C1 must not, it should be strictly less than 1. And because the AR of order 1 requires that C1, the absolute value, because the C1 could be negative or positive. You know what I mean? I said that before. In the absolute term, it should be less than 1 to be stationary. Because it is only when it is stationary that you can actually estimate the mean of the process and the variance of the process. Because we actually also want to know the mean of the process, of the time series process. Not only that, we also want to know the variance of the process, okay? And the stationarity requirement of that is that the absolute value of the C1 must less than 1 to be stationary. We got different kind of tests that can actually use to to conduct a stationarity test. We have different kind of, we got a unit root test, the Fuller test, and augmented test, and so on like that. And I'm actually going to walk you through in the subsequent lecture. But you know what? Now you know how to figure out the mean of the process of the ARO1, you know how to figure out the variance. But right now, how can we do the autocorrelation? I want to walk you through how you can do the autocorrelation at different lag. This is not a white noise model, okay? This is a combination of a signal and a white noise. Of course, in a white noise model, the autocorrelation at any lag is 0. I think you know that. But if it is not a white noise model, of course, you expect to have a different value for the autocorrelation at different lag. And take a look at that. Given this model right now, how at lag 1, how do we find the autocorrelation at lag 1? And what do we mean by the autocorrelation at lag 1? We are trying to look at the correlation between the current value of the time series variable and the immediate past. Okay, so, and you know what is my YT? Okay, my YT is a model. Can you see the model right now? That's my YT, okay? And that is exactly what I'm putting right here. Okay, then YT minus 1, this is YT minus 1. Now, I want to find the correlation, okay? And you know what? What I have right here, I'm actually going to have a 0.9 YT minus 1 plus WT, because the constant, okay, will be left out of the scenario, okay? We got this one right now, okay? And you know what? Based on what I have here, okay, what I have here right now, based on this one and this one, we can actually have this, okay? So this can be splitted into the correlation between a 0.9 yt minus 1 and you know what? This guy here, okay? It's just like I'm trying to talk about this guy, and right here, I'm talking about this guy and this guy. Look at that. That's exactly what I'm talking about. Okay, I think you get it now. Okay, so if that is what I'm talking about right now, is 0.9, which is a constant time, has to come out of that. Okay, so you can consider now that I can find the correlation between the yt minus 1 and yt minus 1. Okay, and you know what is the correlation between a white noise and the current pass under absorption? There shouldn't be any connection, okay? And that is the reason why we're going to write 0, okay? And you know what is the correlation between yt minus 1 and yt minus 1? These are the same variable. The correlation between the same variable is actually going to be 1. So 1 multiplied by 0.9, then I'm going to have 0. So what I have here at like 1, the correlation is a 0.9. Okay? Now, if I want to talk about at lag 2 right now, at lag 2, I'm actually looking at the correlation between the current value and past. Okay, this is like past. Okay, that is what I want to investigate right now. Okay, and similar to what I've done before, you take a look at that, you follow what I've done before. This can be written, the constant is actually going to go away. Okay, then you're going to have correlation of 0.9, okay, the yt minus 1 plus wt, comma, then the yt minus 2, okay, and you know what, I can, the correlation, I'm going to use this one. I'm going to find the correlation between this guy and this guy. Okay, that is exactly what we have here. And I'm going to find the correlation between WT and YT minus 2. Look at that. And just like what I said before, the correlation between a white noise and any lag of the variable or any of the variable, it has to be equal to 0. Can you see that now? Okay, so the next thing now, I actually want to work on this. Now, if I want to work on this, please, I want you to take note of what I want to show you right now. The yt minus 1 is this one. Okay, I need to get the yt minus 1. But you know what? I know that this is my yt. This is my yt. Did you know that from this model, if I put if I want to get a yt minus 1, if I put t minus 1 here, automatically this one will become t minus 2. Do you see that now? And that is the reason why I'm trying to take a look at what I write right here now. So it's going to be yt minus 2, wt minus 1, because what I'm trying to say is that yt minus 1 is equal to all this. Why am I saying that? I'm using the knowledge that yt equal to this. If I put t minus 1 here, then this is going to be t minus 2, and this is going to be t minus 1. Can you see that now? And that is the reason why using this, I can derive yt minus 1. So my yt minus 1, so t minus 1 is going to be this minus 2, because initially this was minus 1. So this is going to be minus 2, and this is going to be t minus 1. And that is exactly what I have inside here. So it means what I got inside here now actually represent yt minus 1. Okay, now what I'm going to do right now, I actually want to find the correlation. Okay, and you know what? Before I find the correlation, I can actually use what I have here to multiply everything that I have here. Okay, but you know what? Is 0.9 times 0.8, it's actually going to give you 0.72. But you know what? We don't deal with constant. Okay, the constant is actually going to go away. And the next thing is going to be 0.9 times 0.9, and that will be 0.9 squared. Okay, 0.9 multiplied by this, I'm actually going to have that. Okay, now when I use 0.9 to multiply all this is exactly what I have. And don't forget, we got a comma, and this is still yt minus 2. Okay, now if I have this one right now, do you know I can look at the correlation between what I have here and the yt minus 2? I can also look at the correlation between that and that. Okay, so with this, And this guy here, take a look at that. The 0.9 square is actually going to come out. Then I'm going to look at the correlation between yt minus 2 and the yt minus 2. Look at that. Then I'm also going to have the correlation between the wt minus 1 and the yt minus 2. And don't forget that I said the correlation between the white noise and any of the variable is actually going to be 0 until you get that. And you know what? The correlation between the same variable is going to be 1. What did I have here? The autocorrelation at lag 2 give me 0.9 squared. A 0.9 squared is a 0.81. And if I ask you to find the autocorrelation at lag 3, if you continue from that, you're actually going to see there's going to be a pattern, okay? At lag 1, I got a 0.9. At lag 2, it's going to be 0.9 squared. Automatically, at lag 3, it's going to be 0.9 raised to power 3. Therefore, by induction, I'm actually going to say the autocorrelation at lag k is 0.9 raised to power k. Okay, that is it by induction. Okay, and that is the reason why I said right here in the generally, when you have the autoregressive model of order 1 that we can also written as this, then the properties of stationarity, when I'm talking about the properties of stationary of AR1 model, this is the formula that you are actually going to use in figuring out the mean. This is the formula you're actually going to use in figuring out the variance. And this is the formula that you are actually going to use in figuring out the autocorrelation, okay? And you know what? And I told you that the absolute value that the autocorrelation, the autoregressive model of order 1 requires that the absolute value of C1 should be strictly less than 1. Let me tell you something. In a situation where C equal to 1, okay, if C equal to 1 right here, what will happen? This will be indeterminate. You remember what you did in your high school? When the denominator of a fraction is 0, it means it is indeterminate. It means I will not be able to estimate, I will not be able to compute the mean, and I will not be able to compute the variance in that situation. Okay, so, and that was the reason why I said without stationarity condition, okay, without stationarity condition, we cannot estimate the mean. Not only the mean, we cannot estimate the variance and the autocorrelation of the time series. Does that make sense to everyone now? Okay. Another thing that I want to talk about today is comparing these three. Actually, want to compare when you have 3 different kind of models. You remember in regression models where we got different kind of models that are competing, okay, where we compare the simpler model with a complicated model, okay. You know that we can also do that in time series, okay. If you take a look at the model 1, the model 1 is a white noise. Let me tell you something. It is not all phenomena that can be predicted. There are some natural. I'm going to tell you something. I want to remember in physics. Has any one of you heard about Robert Brown 1837 when he talked about when he was trying to look at the the movement of the molecules of the particles? I could remember, when he said that, when you subject maybe a liquid to a certain temperature, that the molecules of the particles, they are actually going to be, they're going to be moving. They said they move in a perpetual motion. They move in an aphasad manner. Has any one of you heard about that before? When he was trying to explain the kinetic theory of gases. Have you guys, is there anyone who have heard about that before in physics? Is there anyone who have heard about the movement of molecules. You know, when it said the movement of molecules, it said molecules are moving in an haphazard manner. As, I think I need somebody to, I need you guys to mute. It is only when you guys want to answer a question that you can mute. Thank you so much. Oh, okay. I'm going to read my chat. I think some people put that on my chat. Give me 1 second. I'm actually want to read my chat right now. Okay, so people say, yeah, oh, people, some already say Brownian motion. Yeah, it's Brownian motion. It's good. It's Brownian motion, okay? You know, motion, take a look at that. To me, a Brownian motion look like, have you ever heard about drunkard movement? It's somebody that is heavily drunk. You know, when it's moving. Okay, I want to confirm because I want to have a demonstration. Okay, give me 1 second. Uh, can you guys see me right now? Can you see me right now?
Yes.
Okay, you know, when somebody who is heavily drunk, okay, somebody who take excessive alcohol, okay, and is heavily drunk, okay, and the person is moving, okay, if the person is moving, it's actually going to be moving. It is, you may not be able to predict, the movement of this person. When you are coming along with this person, if you meet the person on the street, do you believe that, when maybe you think he's going to go this way and the person can just go the other way? That's a drunkard movement. That is, we call that a stochastic movement. That is purely stochastic, purely random. We get a phenomenon in life that cannot be predicted. It is not a phenomenon that can be predicted. And what we're trying to say right here now, I'm going to go back to my share. What we are trying to say in model 1 is that let us have a situation where we got a white noise model, purely random process that cannot be predicted, okay? And we have another model that is an autoregressive model of order 1, which is a combination of the signal and the noise. And we get another one is also autoregressive model of order 1, but only that if you look at the parameter here is a 0.9, but the parameter here is negative 0.9. And you know what? They have a different C naught. Although the white noise still remain, the white noise, the variance of the whiteness of the two models is a 0.19. Okay, do you know that we can actually have a way to compare that? Okay, so now if you're going to see what I have, and don't forget the other time we've worked on this model, we've been able to derive, we've been able to see, when we work on this one before, I show you the mean here is 8 and the variance is 1. And don't forget that if you try to do that on and I also show you, I just show you right now, if you take a look at the mode 2, is what I just demonstrated to you. It's also have mean 8 and variance 1. So which means model 1, model 2, in fact, model 3, or if you try, what I need you to do, I need you to follow what I did before on model 3 and see whether you're going to get your mean to be 8 and you're going to get your variance to be 1. Now, if you take a look at the 3 models right here, they get the same mean and variance. If they have the same mean and variance, does that make them to be the same model? And if they are not, which one is going to be the best among them? Okay, now when you take a look at what I have right here, I'm trying to have a plot between model 1 and model 2. Okay, this is a plot between model 1 and model 2. And what I have right here is a plot between model 1 and model 3. Model 1 and model 2 is just like, is there any difference between, the noise model and this one? And the noise model and the other one? That's it. That is exactly what we're trying to do. Okay. And of course, the color of the model 1 is black. And the color of model 2 is red. You can see that now. And that of model 3 is blue. Okay. And of course, you can see what we have here is having a time plot over time, okay? It's plotting the YT over time. And take a look at that, okay? You'll be able to see the clear picture, the way it is spread out over the, the time under investigation, okay? For model 1, okay, and model 2, and then for model 1 and model 3. Look at that. Okay, and if particularly if you look at model 1 and model 3, you're actually going to see that the blue one, take a look at the blue one. The blue one is model 3, and if you look at that, the jump, look at that, look at that, look at the spread. It's more than the model 1. So if you take a look at that, okay, so what we're trying to do right here, we're just trying to compare, the two models, okay, using the time series graph, okay. And you know what? The simulated time series for C1 is 0.9, is the most smooth, and the simulated time series for that is the most jag. And I'm going to tell you why that of, the model 3 is going to be the most jag. Look at that. Look at that. It's the most. Look at that. Look at the jag. It's the most jag. Look at that. And that of the other one is the most smooth. That's what we're talking about. And that was what I said. If you look at the model 2, if you look at the model 2 and the noise, look at the model 2 and the noise. It's looking more or less like a smooth. But when you look at the other one, if you look at the model 3 and the noise, okay, so which means what we want to do in reality is just to compare the model that we have with the noise. Okay, is to compare the model that we have with the noise. Okay, so that's exactly what we're trying to do, and that was why I said the C1 equal to minus 0.9 is the most jagged. Okay, and the 0.9, the other one right here, is the most smooth. Okay, now on a final note before I go away today. Now, how to fit a time series model to the data, okay? What do we need to do when we have a time series data? Of course, what we're actually going to do, I've walked you through how you can obtain the autocorrelation at any lag, okay? And you know what? How can we find the estimated autocorrelation? That's what we call Acf plot. Acf plot is the plot of the autocorrelation. I've walked you through how you can obtain the autocorrelation at lag 1, autocorrelation at lag 2, autocorrelation at different kind of lag. Okay, and you know what? That we can have an Acf plot. What I have here is a plot of the autocorrelation, at different lags. This is a plot of autocorrelation at different lag. Now, let me tell you right now, do you know that if k equal to 0, anything raised to power 0 is going to be equal to 1, right? And that is the reason why, if you take a look at what I have right here, at lag 0, autocorrelation should be equal to 1. Look at that. This is representing 1. Look at that. Now, if you take a look at what I have here, the autocorrelation value is decreasing. Can you see that now? And you know what? And the statistical way to put that is that it's decaying. Okay, and you know what? When you draw an autocorrelation plot, and let me tell you, we got a way to do that in R. What you're going to do on Friday, my TA is actually going to walk you through that. Oh, I want to ask this question. What is your experience of the lab section? Okay, I need you to do something right now, because I'm a kind of person who want to know what is also going on in the lab. I need you to send a message to me when I'm done right now to be able to evaluate, let me just say your experience of the lab, whether your lab session has been good, okay? And if you have any complaint, please, I just want to hear about it, okay? Because it's my job to make sure that, everything under my tutelage or under my supervision is fantastic, okay? So please send a message to me, send it to my email to be able to tell me your experience of the lab section, okay? So like I said, my TA is actually going to walk you through this. So if the autocorrelation decay to 0, then that implies the autoregressive model of order 1. You know what? There are different kind of autoregressive model. We have the autoregressive model of order 1, we have the autoregressive model of order 2, order 3, and so on like that. And what do we mean by autoregressive model of order 1 is that we are trying to build a relationship between, the current value of the series and the immediate past. There are situations where the current AR1 autoregressive model of order 1 may actually be appropriate for my data set. And how am I going to know? I actually need to have an autocorrelation plot, okay, against a lag. And in a situation where the autocorrelation, is decreasing, is decaying, is going towards 0, then that actually implies autoregressive model of order 1. Okay, so I'm going to have an extended class today because I'm going to leave you in the next 7 minutes, okay, because I want to finish this material, okay. For those of you who have lecture at this hour, you could, opt out of the meeting, okay, because everything is captured, okay, is being recorded, and it's actually going to be shared with you at the end of the lecture. Okay, so this is what we call the Acf plot. This is autocorrelation plot. We got a way to, to do this in R, okay? So the only takeaway from here is when the autocorrelation is decreasing, is decaying to 0, then there's an evidence that, the appropriate model is actually going to be AR1. And that was why I said a decaying autocorrelation value may indicate AR1 model. Okay, AR1 model is just trying to say, okay, if you really want to understand the future, okay, what you just need to do, just analyze the current and the immediate past. That's all. That's all it's trying to tell us, okay? In the case of the revenue that I talk about today, okay, if I actually want to predict, okay, the amount that I'm actually going to realize from the ice cream as revenue tomorrow, that we, getting that I only need to investigate what I recorded now and what I recorded yesterday. I need to investigate the relationship between that. Okay, that is actually telling us autoregressive model of order 1. Okay, the immediate past is the one that is explaining, and not only the immediate past and a noise. A noise is a shock on the system. Okay, because no 2 days, no 2 weeks, no 2 years are the same, are exactly the same. There's going to be a shock on the system. From the biological point of view, no 2 human beings, if I want to quote Professor Charles Darwin and Professor Lamarck in the theory of evolution, no 2 human beings are genetically the same. Therefore, in business, no 2 operations will be the same. No 2 days will be the same. No 2